Okay. Good evening, everybody. My name is Saida Said, and I'm one of the TAs for the soil mechanics or geotechnical engineering course under Professor Dilip Kumar Bedia. This is the final interactive session that we are going to have, and in this session, we will not be solving any problem, but we will be going through whatever. It is kind of a summary session in which we will be going through whatever we have studied up till now. Okay, so this was the first week of yeah, this is the first week, and in the first week, if we remember, we studied about okay, this is just general about agricultural and engineering soil. What are the types of soil? Topsoil, organic soil, subsoil, and what is the difference between agricultural and engineering soil? In humid climate, humic acid can be formed when the causing decomposition of humus. This acid leads down to lower layer. They act as cementing agents to form a hard rock-like material, difficult to excavate and does not soften hard pad. Okay, so if we see the profile of the soil, we have fresh parent material or bedrock, which disintegrates due to the activity of various agents, uh, various chemical reactions, physical agents, chemical agents, environmental agents. Due to that, it disintegrates and forms soil over millions and millions of years. So there is a gradational contact in which the rock material, bedrock material, is uh, finally converting into a weathered one second, weathered parent material. Yeah. So the bedrock is this is a gradational um, transition zone. Here we can have a weathered parent material bedrock. This is still not soil. This material is still not your typical soil. Okay. So this material here, what's wrong with my pen? Then you have a zone of accumulation of salts. So what, for example, we see in we used to study about different types of soils, black soil, and these things. Usually, what happens is that, for example, in laterite soils, you have these uh, heavy metals or different constituents that are heavy in weight. What they do over time is, under the force of gravity, they leach downwards, and there is a zone of accumulation of these soils, of these salts, subsoil, and then zone of leaching of soluble salts, topsoil, and then we have a humus in which we have vegetation. We know that we don't have vegetation deep down, we have vegetation only on the topsoil. So this is one of the uh, profiles, vertical profile of soil. And then agriculture and engineering soil the soil geological deposits from the subsoil to the bedrock. Agricultural soil basically is that soil in which you can cultivate plants, which is just the topsoil. Okay. Uh, it has to have a certain amount of nutrition to it. It has to have like those pockets of it has to have nitrogen, oxygen, and all this carbon dioxide, like some gaseous composition, because deep down you will not have this air composition the same. So this is what is required in an agricultural soil. But as opposed to this engineering, these are not basically two different things, agricultural and engineering soil. These are different fields. So when we talk about agriculture, it's a science. Engineering and geotechnique is an engineering science. Agriculture is your we talk about the science of plant growth, nutrition, uh, and all that. We are more fixated on the topsoil, the top layers of the soil. But when we talk about engineering aspect of it, we are less inclined towards what is the nutritional value of the soil. We are more inclined about the strength of the soil, the slope stability, the bearing capacity. Like if we build a structure on it, how much will be the settlement? These are things that are concerned in the engineering soil. And for engineering soil, we consider the whole soil up to the bedrock, because when we load this soil, the load transfer will take place deeper and deeper into the soil. Higher the load, higher will be the pressure bulb over which the area of pressure bulb in which the forces are getting transmitted. So that is the other difference between agriculture and engineering soil. Uh, Let us skip the definition parts. Rock cycle. Yes, this is very important because this is where soils are technically generated. Okay, so there are three kinds of basically rocks um, in the three broad classifications of rocks. Okay, inside the earth, you will have very high pressures, high temperatures, and in this area of very high pressure and temperatures, you get igneous rocks that are very hard. And when weathering of these rocks takes place, uh, you get residual soils, okay, that are like kind of the primary blocks of building of other kinds of soil. So what happens is that these residual soils, due to different actions, for example, due to different transportation agencies, I have this parent material of igneous rock which gets weathered, and I form a residual soil at its own place. Let me check if my pen is working now. Why is this not working? Ah, it's working now. So I have igneous rock that gets transformed into a soil. Now, due to transportation agencies like wind, mm, just a moment, uh, okay, I don't have that. Okay, it's okay. So let's just talk about this for now. So what I can do is I can side by side open another window. Let me try to do that. Just a moment. This is fine. This should be fine. You can see my screen, yes. And what about the recording screen? Okay, this is fine. Yes. So we are talking about igneous rock. We have this rock, and from this rock we get this parent material. And now on this parent material there is the action of many, excuse me, transportate transportation agents like water, there is air, there is gravity. We can have lacustrine deposits. We, if this residual soil is transported through air, we get aeolian deposits. If it is transported through river, we get alluvial deposits. If it's transported within lakes, we get lacustrine deposits. If it is transported under gravity, we get fluvial deposits. Okay, now this was one kind of rock. Now, as the transportation keeps happening, what happens is that it gets transported in layers and layers and layers. And then due to buildup of this overburden pressure, the bottom layers get compressed. They have high compressive forces, so they form these sedimentary rocks that are layered kind of rocks that have these weak planes, uh, parallel planes. So this is the second kind of rock we get, which is the sedimentary rock, in which the sediments get collected and under high pressures they get fused together to form these sedimentary rocks. And then the as we go mm, deeper into the earth, into the below the surface of the earth, below the mean sea level, these rocks again undergo a transformation due to chemical, physiochemical processes, high heat, and maybe chemical processes. These get uh, transformed into metamorphic rocks due to the physiochemical action of these agencies. If you can see here, weathered and transportation, we get sedimentary deposits, and they get weathered and transported. We get sediment like compacted, as I mentioned. The residual soils are weathered and transported. We get sedimentary deposits. Then they get compacted and condensed. We get sedimentary rocks. And then under high heat and pressure of these sedimentary rocks transform into metamorphic rocks. These metamorphic rocks can again undergo weathering and transportation, and they can form sedimentary rocks. And this is the whole cycle. And here, if we see weathering and transportation, if this gets like associated with again magma, molten magma, we get igneous rock. This is the whole rock cycle, how soils are formed. So soils are here deposits, sedimentary deposits, and residual soils. So basically, there are two kinds of soils. When they are formed from rocks, if they are existing at the same place where they were formed, if they exist at the same place that they were formed, they are called residual soils. And if they are transported, they are called transported soils. And when they are transported, they form sedimentary deposits. This is also a form of soil. This is a form of soil. These are the rest are rocks. Okay. Organic soil. Organic soil is a residual soil. Organic soil is not a transported soil. Actually, organic soil means that the soil, what, for example, you have a sedimentary soil, but you have a lot of vegetation in that area, and due to that vegetation, the soil is getting mixed with this vegetation, these fallen leaves, these roots, these plants that get buried, isn't it? This they basically are not transported, these plants and everything. You think about it, if they get transported through water, the organic matter will disintegrate, isn't it? But you do have uh, uh, transported soils that are organic in nature. But the parent soil is basically transported, that like you have alluvial soils, but the organic matter is from the source, from the destination area. Organic matter will be due to the um, plants and for flora and fauna of the area at which the soil has been transported. Uh, are you understanding what I'm saying? See, what I'm saying is you have two kinds of soils, residual and transported. In residual soil, what happens is this is your bedrock, and then this is this transition zone, and this is the soil, residual soil. Okay. If this residual soil gets transported to another, if this is bedrock A, this is bedrock B, this will be residual soil A. This will have a residual soil B. But some of the soil from A is getting transported and deposited. We will have a transported soil A. Okay. From this bedrock, soil is getting transported here. But if I am saying that I have an organic soil, it means that there has been vegetation here. So this organic soil A will be, so this soil A will be organic. But when it gets transported, uh, let us for instance say that there is no vegetation here. Okay, this is not an inorganic soil. Okay, but when it gets transported here, it gets transported to an area that has high vegetation. Okay, so what happens is that it may have uh, organic matter due to this area, but it may originate from an inorganic origin. Okay, next thing, next question. Sorry, next part. Rocks are made from various types of minerals, and minerals are substances of crystalline form made up from a particular chemical combination. Main materials in rock include quartz, feldspar, calcite, mica. Geologists classify all rocks into basic groups: igneous, sedimentary, and metamorphic, that we have just mentioned. Igneous rocks have become solid and melted from a melted liquid state. High temperatures, high pressures. Extrusive igneous rocks are those that arrived on the surface of the earth as molten lava and cooled. Intrusive igneous rocks are formed from magma that is found itself through cracks into the rock beds below the surface and solidified there. Okay? And then there are some examples. See, I'm going a little fast because there is a lot to cover in 2 hours. So I will be moving a little fast and I will be focusing on some um, more important points. So sedimentary rocks, as I mentioned, is due to sedimentary rocks are due to transportation, sandstone, chalk, shale. Metamorphic rocks, through high temperature and pressures acting on sedimentary rocks or igneous rocks, we produce metamorphic rocks. Okay. Soil formation from rock, it is action of various environmental agents like frost, temperature, gravity, wind, rain, chemical weathering. And we have a transported soil that we call mentioned here. For example, there is a flow of water, erosion takes place here on the bedrock, and this gets deposited. And if you see here, this is kind of a uh, we used to have this kind of you see when we talk about filtration, we or separation, we do that gravity mass based separation. That this is a natural process of separation in which when the water is flowing, the heavier particles will settle first. The heavier particles will settle first. Yeah, and the lighter particles will settle far. That is how uh, that is what you find in along the rivers. See, rivers will have an alluvial basin that is very fertile, but if you move farther and farther, you have that khadar soil and the bungar soil, which is this is coarse gravel, this is fine gravel, but as you move towards the water body, you will have finer and finer, even till clayey soil. This is the natural way of separation and gradation of soils. Okay, transported soil. Yes, please. Yes. Yeah. Yeah. River transported soil. That is, yeah, yeah. But this is, you see, the river is extending in the direction along the plane, perpendicular to this plane. Okay. So you will get a band of clay, you will get a band of silt, and you'll get a band of gravel. Yeah. 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 Yes. 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 Due to turbulence. Mm, that yeah, I think see delta is a combination of two or three rivers. Okay. So one river will have its own uniformity, other river will have its own uniformity, but based on the speed of water on those rivers, maybe when the river A is moving towards a location, the gradation is has reached like sands are like gradation due to river A will not be equal to the gradation of due to river B. It may be different, isn't it? And when they meet, they may have different. Uh, yeah. Okay. So transported soil are Louis that are transported due to air. Again, you will see a gradation in these. Residual soils are those that are left behind uh, at the same place at the parent material, and laterites are soils that in which you see leaching of minerals from the top to bottom. So they will be essentially some. chemical, some chemicals absent from these soils. Okay, and then organic soil is that has a large amount of decomposed animal or vegetable matter, usually dark in color, give a distinctive odor. Uh, Usually being created. Silts that have been usually created from river or lake sediments. Peat is a special form of organic soil, which almost entirely consists of lightly fully decomposed vegetable material. It can be fibrous, pseudoplastic, or amorphous. Engineering, in engineering sense, when we talk about granular soils and cohesive soils. Granular soils are sands and gravels, and cohesive soils that have cohesion are clays, and not even silts. Silts have very low cohesion. Clay minerals are kaolin, illite, morillite. Okay, soil versus other engineering materials. We know these properties. We have already talked about the heterogeneous material of the soil. For example, you have some man-made material that will be homogeneous throughout because you have mixed it that way. You have made it that way. But soil, because it's a natural material, it will have many different kinds of inhomogeneities, and these materials when you make they are usually isotropic, but the soil, because it is a layered formation, uh, for example, when we talk about formation of, let's say, even man-made embankment. When I'm making an embankment, first I'm taking one layer and compacting it, let's say with force 1. Then I'm taking another and compacting it, let's say with force 2. Then I'm taking another layer and compacting it with force 3. As you can see, the more and more compactive effort is being delegated to this layer as compared to this, as compared to this. So the properties, even the density, the stiffness, the friction angle, um, not the friction angle, but yeah, the properties that are attributed to the unit weight will be different for this layer and they'll be different for this layer. And as you can see, that void ratio will be different. And you know that permeability is dependent on void ratio. Now, when you take water here and we draw this flow net, you can see that this is not an isotropic material. It will have same properties in this direction, but it will not have same properties in this direction. It will have different kV, kV1, kV2, kV3. You understand what I'm saying? Yeah. So, soil characterization, we talk about soil permeability, we talk about soil compressibility and shear strength. And let us, okay. So, the first thing is we need to let's recap what we studied in the whole soil mechanics one. First, we studied the weight volume relations. Then we studied the index properties. So this is the introduction. Then we studied effective stress and pore pressure. So we are building our profile from zero. Let us say we don't know anything. Let us say we don't know anything about soils. So we start talking about, firstly, if I give you a soil, what is it that you can tell me about it? To a layman. To a layman, or somebody who is not geotechnical engineer, to a layman, what will you speak of? and I give you a soil sample, you talk about, as a layman, you'll talk about the color, the odor, the texture, the maybe water, not water. These are the preliminary tests for soils. What is the color of the soil? If it is red, we can say that it may be laterite because laterite soils have iron deposits. If it is black, we can preliminarily say that it may be organic because the organic matter gives blackish color. If it is, say, very light in color, chalky, we can say that it may have some calcium deposits. And smell, if we talk about the blackish soil will have, the organic soil will have some kind of a pungent odor. So that is the first thing. So we're trying to start from the basics. This is the first thing you will see about the soil. Now, let us move on to a more systematic and engineering perspective. Secondly, I tell you that what else can you tell me about this soil? Or can you do some tests and give me a little bit of information about this soil? So, what we can do is it can be the soil that I have given you. First of all, you ask me, is this a disturbed sample or this is an undisturbed sample? If it is a disturbed sample, it means that, yeah, yes, Rafi, I see a raised hand. Okay, you can, okay, it's okay. Okay, yes, please. Yeah, okay, okay, okay. So let's not write. Okay, okay, okay. Yeah, thank you. Okay, so as I was saying that if you have for example, if I give you a soil sample, you'll ask me if this is a disturbed sample or this is an undisturbed sample. Why you'll ask me? Because say if this is an undisturbed sample, there are many things, many tests that will not matter then. For example, if I do a density test on a disturbed sample, it will not give me anything. It will not give me any idea about the kind of soil because density test you do on an undisturbed sample because you want to know that at what density is the soil present in the field. But if I take a heap of soil and I give you and you do a density test, it will not matter. However, it will matter if you are, for example, talking about a minimum density or a maximum density test, like in sands that we do. Minimum, what is the minimum density that this sand can reach, or a maximum density? But I think I'm getting off track here. But okay, field identification of soil. This is what I was actually just saying. Sands okay. Uh, Sands are individual particles. We have not discussed clay here because it is greater than so not clay, gravel. We have not discussed gravel here because that is more of a transportation kind of thing, and usually we don't do constructions on gravels, and they're more related to subgrades and roads. So when we talk about soils, we usually talks about sand, silt, and clays. And the how you identify in field individual particles are visible, that we already know. This exhibits dilatancy. Do you know what dilatancy is? Rafi, have you studied dilatancy in this course? Yeah, same thing, same thing. Yeah. So in this course, you have already discussed it. Yeah, from the critical state perspective also. Okay. Yes. So, in shear strength, we have covered about the die latency. When you have when you have dense sand deposits and you share them, you can see increase in volume instead of a decrease in volume. Like in loose sands will decrease in volume, but in dense sands, you will with sharing you will see increase in volume, which is called die latency, and this is not seen in clays. This is only seen in sands and silts. And now we know that we say coarse grain soils and fine grain soils, and we demarcate it at 4.75 and the 75 micron. But silts, even though they are fine grain soils, but they are non-cohesive. Only clays are cohesive. So there are many properties of silts that are more closer to the behavior of sands than to clays. So when we talk about fine grain soils and coarse grain soils, it is not a very good what we can say, it's not a very good demarcation of the two kinds of soils. We should say cohesive and non-cohesive soils, because coarse grain soil is sand, fine grain soil is silt and clay. But silt is more closely, behaviorally more close to sand, because it is non-cohesive. So we can say clay as cohesive soil and silts and sand as non-cohesive soil. Easy to crumble and falls off hand when dry. Easy to crumble, can be dusted off when hands. Hard to crumble and sticks to hand when dry, because of cohesion. Feels gritty, the silt feels rough, while the clay feels very smooth. The sand has no plasticity. Silt can have some plasticity, and clay is highly plastic. So mechanical sieve analysis, that this is done for cohesionless soils. This is not done for cohesive soils. We take these different soils. We take the different sieve sizes and we pour our sample from the top and we shake rigorously. Uh, so there are, is it mentioned? No, it's not mentioned. There are basically two types of sieve analysis. It's with wet sieve analysis and dry sieve analysis. Sometimes what happens is that because of cohesion, if you have a soil that has both cohesive and non-cohesive particles, the cohesive particles will stick to your non-cohesive particles. However much you will shake these particles, they will not come off. So in those cases, what we do is we do perform a wet sieve analysis, in which at every level we will wash the particles off. Okay, the fine first we will like that is how the wet sieve analysis is done. Then the particles are dried and then weighed, and then you get your particle size distribution curve, and it significantly it's not a small amount of particle that is sticking. If you actually perform dry sieve analysis and wet sieve analysis on the same soil that has a significant amount of fines, you will see that in the first case you might have gotten only 10% finer material, but when you did the uh, wet sieve analysis, you can get as high as 50% finer material. Excuse me. So from the sieve analysis, we try to calculate the weight retained on each sieve size, and we then calculate the percentage finer than this weight. The sieve size, the sieve size is actually the diameter of the opening of the sieves, and from that we can get the particle size distribution curve. Yeah, if you can see here, we get a particle size distribution curve, uh, in which is on a semi-log paper, and here you will have cohesive soils and cohesionless soils. Silt is not cohesive. as far as I know. One second. Yes. Uh, yeah. Yeah. And also, I think there is something wrong with this because uh, I also think that the cohesive soil that they have mentioned here is not correct because I don't think silt is cohesive. Sometimes, yeah, but I don't think we can call it specifically cohesive soil. Yeah. Okay. Okay. So we take so here if you see at 75 micron, this is 0.01, 2, 3, 4, 5, 6, 7, 5 up till here almost. This is soil A, this is soil B, and this has the soil A has 70%, 75% material finer material, while soil B has almost 35. So this is a coarse grained soil, while this is predominantly a fine grained soil. Can you see? One second. Okay. So that was about the sieve analysis we do for fine grains for the particles greater than 75 micron. But what about particles less than 75 micron? So for particles less than 75 micron, especially, we can't have that. We do have. There are some ultra micro sieves that can actually go up to, I think, 2 micron, not 2 micron, yeah, something like that. But first of all, that's very unnecessary, not unnecessary, but yeah, they are equipments. But the thing is that if your soil again is cohesive, it will stick. First of all, the particles lesser than 75 micron, if they are cohesive, if they are more or less silty and they are not so cohesive, then you can go for that ultra micron sieves. So, uh, but generally for less than 75 micron, we have the hydrometer analysis, which is based on the Stokes law, which states that infinitely falling particle will achieve a terminal velocity. So we have this hydrometer, which basically calculates the specific gravity of a material. So the hydrometer at the center. So what the hydrometer is doing is that it is telling you, the hydrometer reading will tell you the specific gravity of the material here. And we are assuming that the material that we mix in the hydrometer, that is falling, or it gets stratified in a sense that as it is falling, it gets uh, separated based on the size of the grains. What we are assuming is that all the grains have same. Yes, I think. Yeah, 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 yeah. That is the principle behind the hydrometer. Yeah, yeah, yeah. It should not be lower than that, because one it will show one with water. Yeah, I'll have to check that what is the range, but I think there are different ranges of the same principle. For the same principle, you can get different ranges, the different sensitivities. That if you want a very sensitive hydrometer, like so you can get that also. Um, Specifically for soil, it will be a little based on what are the values that we specifically encountered. So, yeah. So we are assuming that the specific gravity of all the soil particles is same, okay? Which means that gamma S specific gravity, oh sorry, GS is equal to gamma S by gamma W, है ना? And yeah, what will be, no, I'm continuing the lecture. Okay, so gamma S is the weight of solids over volume of solids. Okay, weight of solids will be your depending on your GS, which will be uh, and volume is dependent on the shape of your particle, isn't it? So based on that, the smaller particle will have lower mass, the larger particle will have greater mass, and they will settle quickly, and lower particles will take time. And we calculate uh, the specific gravity at different times, and from the time we correlate what should be the size of the particle based on the specific gravity. Specific gravity, you already have to know about this material. Uh, Based on this, uh, we take a spherical volume here, okay, based on specific gravity and the terminal velocity. We calculate the diameter of the particle at um, uh, like different what can I say? Sorry. We calculate the diameter of the particle, and from these values, we calculate the percentage finer than from this formula. Okay, there are some corrections also that we do in the hydrometer test, and they are due to first of all the meniscus correction, because lower meniscus, upper meniscus, and then there is the correction due to temperature, and then there is a correction due to the uh, deflocculating agent that you have added. Okay, deflocculating agent that you have added. Okay, then so the reason for doing this particle size analysis is to grade your soil, like what are the different particle size of particles and by how much amount. Uh, and now we are talking about some quantitative values uh, that can help us select soils for engineering applications. This is a coefficient of uniformity and coefficient of Cc. D60 is the particle size below which, if we talk about this, D60 for soil A is 0.04. Okay, D10 for soil A is, this is 0.007. Okay, so 10% of the particles in soil A have a size lower than 0.007. 60% of the particles of soil A have a size lower than 0.04, and D30 is here, and this will be 30% of the particles have a size lower than 0.015 almost. Okay, so we calculate these values and we get these coefficients, coefficient of uniformity and coefficient of curvature. So the coefficient of uniformity will tell us about the gradation. Coefficient of uniformity, is it a well-graded soil or is it a poorly graded soil? And coefficient of curvature will basically tell us about the angularity of the particles or the shape of the particles. Okay, and then, yes, please. Yeah, gap. Yeah, gap graded soil when we get, for example, if we, one second, when we have, for example, a gap graded soil like this, okay, you have a 60%, for example, here, there is a long range, yeah, there is a long range of diameters that are already, that are actually uh, absent. Yeah. So the thing is that in these soils itself, you know that this is not a uniformly graded soil. And CC and CU, you are calculating to see if it is a uniformly graded soil or not, isn't it? How is the, yeah, yeah. I I actually do not know that. Do you have any information on that? Okay. Yeah, I understand that. But the question also arises, Rafi, is that why do you want to calculate the uniformity? If you're saying that you want to calculate the CU and CC for reasons other than, if you want to calculate the D10, D60 for reasons other than CU and CC, for example, you have a correlation between permeability and D60, you have a correlation between CC and D60, because of that, if you want to calculate, that is a valid point. But for CC and CU, if you want to calculate, I would say that you already don't need to calculate because you already know that it is not a well-graded soil. You understand what I'm saying? Then it is okay. CU, CU, CU. Okay. Yeah. Okay. No, you have two. You have No, no, you have two parameters. You have a CU as well as a CC. See, for example, if we talk about this soil, D10, one second, let me first erase all this. Yeah, let us redraw. You're saying that let's redraw at D60. Yeah, where do you want the gap to be? Okay, okay. Yeah, I I understand your point. I understand your point. Yeah, yeah. I understand your point. But what I am saying is that, Rafi, why do you calculate CU and CC? Yeah. What is the end point you get when you calculate CU and CC? Yes, yes, isn't it? So, one second. What I am saying, what I am, t I understand, but listen what I am telling you. I'm telling you that D10, this is not writing. Okay, D10 is an important parameter which is related to many of other, like, for example, permeability. It's related to your that when you talk about your pore water pressure, that tensile stresses, it's related to that, isn't it? But if for that, if you want to calculate D60, that is that is a valid point. But here, when by visual observation you can see that this is a gap graded soil, why do you want to calculate CU and CC? CU and CC will, yeah, yeah, yes, okay, okay, that, okay, okay, let us uh, put a pin on it. Yeah, let us put a pin on it and let us discuss it. Okay, I will definitely get back to you based on this. Okay, so that was about coarse grained soils. Coarse grained soil, you talk about if it is well graded or poorly graded. Poorly graded is if it has either uh, some of the gradations, some of the diameters are not present, or either only one kind of diameter is present. So that uniformly graded or gap graded, they are poorly graded soils. Well graded soil, it has a good amount of particles in all the diameters. That is how you classify the coarse grained soils. But when we talk about fine grained soils, we do not use these parameters CU and CC. We use different parameters, which we call the consistency limits, which are the liquid limit, plastic limit, and the shrinkage limit. From this diagram, we can see if the material uh, these are performed on remolded samples. It is not performed on like your fresh sample, like you do your density. No, it is performed on a remolded sample. What you are saying is that you're talking about the cohesive properties of the soil and how you are doing it, that you're adding water to it and you're saying how much water it takes for this particular soil to become completely a slurry. Okay, you make this soil into a slurry. If you make this soil, that is not how the tests are done, but this graph shows that if you make this soil into a slurry and then you start decreasing the water content like this, what happens will that is that because the soil here, one second, is this not working? Okay, because the soil here, when we talk about, let us take a representative elemental volume, REV it is called. If you take an REV of the soil, there is so much water present in the soil that uh, many of the much of the volume that usually is occupied by soil is right now occupied by water. Okay, it is oversaturated. Okay, so as you reduce the water content, the volume of the soil will reduce. Okay, and as you go on reducing up till here, up till the shrinkage limit, at the shrinkage limit, that is the max, that is the minimum amount of water that you need for saturation. That is the perfect saturation, and anything over this will be oversaturation. It means that this increase in water is due to this increase in volume is due to the addition of water, and below this, the this is the minimum volume of the soil it will have. Below this, the water is only present. This water is only present in the voids, and the shape of the material is actually determined by the pore structure of the soil, not the water. So as you go on decreasing, you will get a constant volume. Uh, from here to liquid limit is the maximum it is the minimum water content at which you will have zero shear strength. It will become a slurry after that. It will not give you any, like, you cannot walk on water, but you can walk on soil. But when you have, for example, there is a lot of rain, you have that muddy kind of soil, you feel like you cannot walk on this. Why? Because it has become a slurry, it has lost its shear strength. And this point is where it loses all its shear strength. And below this, shear strength is increasing. Okay, shear strength is increasing, water content is decreasing, and in this area, the soil is plastic, and it's called plastic because uh, it is like you can shape it into anything, like the potter's clay. And as I said, that we have, as water content increases, load carrying capacity, uh, water content increases in this direction and load carrying capacity increases in the opposite direction. Means as the water content increases, load carrying capacity decreases actually. Okay, so we have a liquid limit, plastic limit, and shrinkage limit. In this region, the soil is brittle. In this region, it is semi-solid. This is plastic, and this is total slurry. Uh, and yes, no, no, no. I really like it. I really appreciate it. Uh, yeah, yes, yeah, 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 yeah. I can see that. I can see that. Yeah, yeah, I can see that. Okay. So next we talk about the stress-strain relation. So at stress-strain, like we talk about soils, this will be a brittle solid. It will fail very mm, suddenly. Okay, this is uh, when your water uh, when your water content is less than your plastic limit. You will see not exactly plastic failure. This will be between plastic limit and liquid limit. Plastic solid, you will have a failure like uh, that you can more of a, you can say, smoother curve. Okay, this should have been a little bit. One second. This should have been a little bit like Oh no, my screen is not responding. What I meant to say was that the graph should have been a little bit more steep with an abrupt failure point. Yeah, yeah. And then the second graph, you can see a more smoother transition, which is the plastic when the soil is in the plastic range, and when the soil is when the water content is greater than the liquid limit, you can see that there is technically no strength in the soil. But 1 second, I have to. Actually, this is a. If you can see my pointer, this has. Yeah, not even showing. Okay, so this is what we talked about. Liquid limit, this is the test for liquid limit is the Atterberg's. This is the yeah, Casagrande apparatus. I will not go through the how the tests are conducted because as I can see that we don't have much time. 1 hour is already over and we are much behind. Uh, Let us talk about based on classes, soil classification based on plasticity index. We have a non-plastic, low plastic, medium plastic, and high plastic soil. But the main use of these plasticity indices is in the soil classification system, in which we have that A line, U line that helps you in gradation of in classification of the soil. Other use of this is in you have these formulae. For example, Cc is equal to 0.007 into Wl minus 20 and something like that. Uh, huh. So you have these formulae throughout the literature based on the liquid limit and plastic limit and everything. And this is the consistency. Uh, these are called consistency limits because based on the water content or based on the liquid limit, plastic limit, and sink rate limit, we can say that what kind of consistency the soil has. Is it plastic, semi-solid, solid, or liquid? This is the plasticity charge that I was talking about. We have this A line in which we have when we try to classify the soil. First of all, what we do is we try to see if 50% is more than we take a sieve at 75 micron and we sieve it. If 50% is more than 75 micron, which means that if 50% of the material is lesser than 75 has is finer than 75. Sorry, I'm saying more and less. If 50% of the material is finer than 75 micron, we can say that it is predominantly a fine-grained soil. And if it is greater than 75 micron, we can say it is a coarse-grained soil. And the second step is that once you have identified if it is a coarse-grained soil, then you will go for gradation test. It's well graded or poorly graded. And if you have identified that it is a fine grade soil, then you go for consistency limits. And from consistency limits, what you do is you calculate this plasticity index of the material. It will lie anywhere, it can lie anywhere, na? So you will have a liquid limit, you will have a plasticity index. For example, it lies here, you will see that it is below the A line. It can lie here. The equation of the A line is given here. Okay, you can have this equation, and then you check against your soil where the one second, where the uh, point lies on the plasticity chart. If it is above airline, then it is a clayey soil. If it is below airline, then it is a silty soil. And then we have these demarcations based on the liquid limit. If the liquid limit is greater than 50, then it is a highly compressible silt, or if it is between 35 to 50, medium compressibility, and it's lower than 35, then it is a low compressibility silt or clay. Yeah, yeah, yes, please, yes, please. Yeah, yes. I I think that there have been researchers that have used this material to classify their material. Now, because usually you usually in fly ash we have that triangular. You remember? I think you must know about it. Yeah, you have. Yeah, you have a textural classification. I think usually in fly ash we use that, which is not very, yeah. Uh, you can. I'm not saying you cannot, but it is a better. There are better ways of classification of blended materials. As I said, that there are these tetrahedral charts that na. I will I will show you. I will show you a chart. If you talk about is it possible, then why not? You can. But problem is not that. Problem is that these materials are usually non-plastic. If you talk about fly ash, it is non-plastic. You will not have a plasticity index in that. Okay, because they have this blended. Yeah, yeah. In research, these parameters have been calculated for blended materials, because I have gone through many papers that have calculated the liquid limit, plastic limit, and everything for blended materials, not for the pure material, like only fly ash, it maybe they won't have. But when they blend the soil with fly ash, lime, maybe even red mud, sometimes slags, even gypsum, they do calculate these values, because what it does is that it creates a standard, like how you can compare the performance of only taking soil and then taking a different material. Comparison, it creates a comparison. Maybe the tests in themselves will not have any kind of significance, but when compared to soil alone, they can give you a comparison of the behavior of the soil when blended with other materials. Okay. So next we can talk about classification systems. Uh, we will talk about the Indian class. There are so many classification systems, but we will talk about the Indian classification system. In Indian classification systems, we have two letter system. One to define soil type, second to define the subgroup. For example, SP is polygraded sand, SM is silty sand. Okay. So basically, if you have greater than 1 second. Let's go through the steps first so you will understand what I'm saying. Determine whether the given soil is of organic origin, and organic soil identified visually by its color. Okay? If 50% or more the soil weight is retained on 75 micron, it is a coarse grained soil and it is not fine grained soil. Um, if the soil is coarse grained, and if 50% of the coarse grained fraction is retained on 4.75, it can be called as gravel, otherwise it will be sand. If the fraction passing the 75 micron scale is less than 5%, we can have Cu or Cc from the particle size distribution curve, and we can say it is a well-graded or poorly graded soil. But usually this is not the case. You will have a soil that has a 12%, more than 12% fines. So in that case, what you have to do is you have to do uh, uh, if it is more than 12%, then you have to do the liquid limit and plastic limit test, and from there you have to determine if the soil is silty, if the fine soil is silty or clayey, and from that you can say it is GM, SM, GC or SC. And if it is between 5 to 12%, the soil is assigned a dual symbol. Uh, like what it's trying to say is that once you are taking 50%, 50% 60% of the soil that you have taken is coarse grained soil. Okay, the second step is from the 60% C, which is majority gravel or sand. Let us say that 90% of this 60% is sand, so that means that it is a sand. Now you will take Cu and Cc for this sand. But first let us see that how much is the fine particle. Fine particle was 40%. Okay, if the fine particle was less than 5%, you could have only talked about the coarse grained soil. You could have only said based on the Cu and Cc. Let's say it is well graded, we could have said that it is SW, well graded sand. But if the soil particle has a higher like it's greater than 12%, the mm, um, fine grains are greater than 12%. Now you will do the consistency limits and you will identify if it is a clay or a silt. Okay, and you will give the you will give the symbol G. For example, it is silt, it will be a SM. Okay, and if it is between 5 to 12%, if it was greater than 12%, means that uh, it mattered that if it is a silt or clay, because it was in a greater content. So you were basically saying silty sand, means sand and silt have like the silt will have a good mm, effect, a good what I can use the word influence on the material's properties. But if it is between 5 to 12, then you give a dual symbol uh, for the sand and the clay. You For the clay you give for the fine grained particle you will give the compressibility, and for the coarse grained particle you will give the gradedness. Okay, that is about and we also have a classification system for sands. We talk about the relative density. So what happens in sands is that this is a very important property in sands. This is not something we calculate for clays. What this means that uh, a particular sand that you have, uh, it will the shape of the particles is will be such that because the sand itself is a loose material, it under vibrations, under vibratory loads, it can compress, it can densify, isn't it? and under even earthquake loads, it can even like loosen up. So usually in construction, we take some sands from the sample pits. There is a minimum void ratio that a sand can have. If you vibrate it excessively, there is a minimum void ratio that it will have. All the grains are perfectly aligned such that there is a minimum void ratio. So that is the E minimum or the maximum density that this particular sand can achieve. And there is also a minimum density or the maximum void ratio. If you simply pour the the sand from a height, it will be in its loosest form. So these are two properties of the sand that you calculate in a laboratory, and then from the actual void ratio in the field, you can say how much relatively dense this particular deposit is. This is usually used in compaction studies. Okay. So if you can see here, this is the whole entire range of void ratios that the sand can have, and this is the relative void, the void ratio relative to the maximum void ratio or the loosest state, and you take the ratio, it will get you an idea about at what point your soil. Actually, let me show it here. So over the scale, you have E minimum and you have E maximum, and this is the entire range of soil of void ratios that your soil can have. For example, it is at E here, and this is E. Let's say this is maximum, this is minimum. Okay, so we are taking this ratio. This ratio will always tell us about the relative density of the soil. This is what we use as a control in compaction studies. Okay, so if it is 15%, it's very loose, 15 to 35 loose, greater than 85, very dense. Okay, so next is the three-phase diagram. We are talking about the description of soil, which can be described in actual form is this. What we try to do is we try to compress all solids here and all the voids above, and the voids can itself be filled with water and air, so we can have a three-phase diagram. And these are the weight volume relationships that I talked about at the start. Void ratio is the volume of voids. Let's not do it that way, it will take a lot of time. uh, Porosity and void ratio are basically related to each other, and void ratio will tell us about the structure of the pores of the materials. Like a dense soil will have a lower void ratio, and loose soil will have a higher void ratio. And the void ratio can what all can a void ratio tell you about a soil? Once again, a void ratio can tell you about the permeability of a soil. A soil with a higher void ratio will have a higher permeability. A void ratio can tell you about the even strength of the soil, because in loose sands the void ratio will be high and the strength will be low, as compared to dense sites will be void ratio will be low and the strength will be high. It can tell you about what else can it tell you about? Think about it. Yes. Yeah. Yes. Yeah. Yeah, yeah, it cannot be zero. Yes. Yeah, yeah. It means that it will mean that the soil is no longer a porous material and it is a solid material. Yeah, yes, that is true. True, true. No, no, it cannot. It cannot be zero. Yeah, yeah, yeah. What? Yes, yes. You are correct. You are correct. What you are saying is correct. What when only for sand. Yeah, yeah, yeah. But what I mean to say is that when you compare same soil, if you're same clay, even in cohesionless material, same material, if you compare with a lower and a higher void ratio will have a higher permeability. That is what I meant. Yeah, that is what I meant. I'm sorry. Uh, I, w- I will ask them to. Okay, okay, okay. Okay. So we are talking about a three-phase diagram. Yeah, we're talking about a three-phase diagram. Why we talk about a three-phase diagram is because the voids of the material are filled with either two kinds of fluids. Okay, both air and water is a fluid. So there are two kinds of fluids, basically three phases. There's a solid, water, and air. And these are the three phase diagrams we study. The dry soil will only have air in the voids. The saturated soil will only have water in the voids, while a partially saturated soil will have solid air, water, and air. So degree of saturation, again, if we talk about, is like telling you about, just as I showed you. I just wish it would work. Yeah. Uh, Degree of saturation, if we talk about, if this is the volume of voids, this entire will is the volume of voids. If this entire area, if this entire length is the volume of voids, the volume of water is somewhere here, isn't it? Again, this is a comparative. Like this is, I'm showing this because usually this is how I visualize things. Uh, this is true for this kind of visualization. Degree of something, when you talk about degree of compaction, we talk about degree of saturation, we talk about degree of consolidation, isn't it? It is always a ratio like this, in which in the denominator you have a range, the entire range that the particular property can take value from, and then at the numerator you will have the present uh, value of that property. So it will be the degree of that property from the entire range of that property. That is the degree of saturation. That is how I usually visualize. So I thought maybe I should extend it to you people. Range from 0 to 100%. Degree of saturation is 0 for completely dry, 100% for completely saturated, which means that 100% means that volume of voids is equivalent to volume of water. And if you see it on the scale, it will be, as I said, uh, if this is volume of voids, which can start from 0. not from 0 but just greater than 0, and this will also be the volume of water, and it will be 0. uh, we can say volume of void max, volume of voids minimum. Okay, no, you cannot say that. It has to be this this particular measurement is itself volume of voids. Okay, so volume of void, this particular measurement divided by this measurement. When it is 0 means volume of water is 0. If it is 1, it means volume of water is here, which is this case, and S is equivalent to 0 is this case. Then we talk about density. We already know density is the mass over volume, and we talk about unit weight, which is weight over volume. Okay. Uh, then we talk about bulk density. Bulk density is total solid plus water over total volume, which takes volume of solids and volume of voids. And we have this relation that we have talked about extensively in the interactive session. Saturated unit weight means that all the voids are filled with water. Okay. Uh, Gamma saturated, you can we have gone over this. Gamma dry is when all the voids are empty. SR is 0. Okay. So you know this relation GW is equivalent to SE. So for gamma saturated, S is equivalent to 1, and gamma D, S is equivalent to 0. Or W is equivalent to 0. And we talk about submerged unit weight. Submerged unit weight, as I've already mentioned, you will only get submerged unit weight when you are talking about soil under groundwater. Saturated soil itself does not account for submerged unit weight. If you have two soils and you have groundwater here, if you have a soil and you have groundwater here, soil here is saturated, the above soil is saturated, but when we analyze it, we will not take this soil as submerged. Effective gamma effective, we will take as gamma saturated. While as for this, we will take it as gamma submerged, because under groundwater you will have a buoyant force. Above groundwater you will not have a buoyant force. And gamma submerged is usually gamma saturated minus gamma W. It's almost gamma saturated minus 10 if you are taking in kilonewton per meter cube. Three-phase relationship. Okay, let's not go over these relationships. We have already talked about these relationships, and these are some questions on these relationships that we have talked about in class. Now let's talk about seepage and permeability. Uh, so in what forms we have water in soil? We can have groundwater, we can have um, like groundwater, we have subsurface water, we can have water associated with soil, as in uh, normal water in the soil. We can have bound water, we can have uh, capillary zone water. So these are the different types of water that you have. All water found beneath the earth's surface, the main source of tropical rainfall percolates downwards. Okay, saturation zone. uh, okay, water table. Okay, yes. Okay, water table and ground surface. Usually, water table will uh, wait. Why this will happen? For example, you will have a bedrock here. Why the water is not like this? That is because of the pores of the soil that we have, the suction that is created in these pores when it is in equilibrium with the atmospheric soil, well, atmospheric air. It will create it is based on this elevation of the ground. That is why it will gently, ever so gently, mimic the shape of the uh, ground surface. Okay, aeration zone, capillary fringe. Yeah, aeration zone is at the top of the water table and can be split into three sections. Zone occurs between the water table and the surface, which means where the voids are have some kind of air. Okay. It can be a capillary fringe. Capillary fringe is just above the groundwater table because of the suction produced due to the atmospheric air, and not due to the atmospheric air. The suction produced due to the tiny size of the pores. There is a capillary fringe just above the water table in which the soil is completely saturated, but not acted upon by any buoyant force. You should remember, it is completely saturated. It is called capillary fringe. Then the intermediate belt, as rainwater percolates down the water, a certain amount is held in the soil by the action of suction tension, capillary adsorption, chemical action. This is retained in this manner is termed held water, deep enough not to be affected by plants. Okay, it is just above this capillary fringe or along this capillary fringe. Then there is a soil belt zone constantly affected by evaporation. Yeah, so, and as you know, the cycle, the water cycle, there is always evaporation, condensation, rainfall, transpiration. This is plant transpiration. So that top soil in which the water is always affected by the weather conditions. This is the soil belt. This is soil water in atmospheric equilibrium is called hygroscopic water. I don't think this is correct. I'm not sure if this is correct, but from what I know, hygroscopic water is the water that is held by the soil and is not uh, available to the plant, or which is not available for taking unless and until you are performing your expending a high amount of energy. Okay. No, I think hygroscopic is water is the held water, like just a film around the particles of the soil, and it cannot be extracted by the plants. It's some there is a when you talk about unsaturated soil mechanics, there is this field capacity, and then there is this residual soil moisture content. The residual moisture content, you cannot suck it out anyway. You cannot dry it, you cannot suck it out. That is the hygroscopic water. It is not the vapor pressure. Uh, Most soil in contact with the atmosphere either evaporates or condense water until its vapor pressure is equal to the atmospheric pressure. Soil water in atmosphere, I think when it is in equilibrium to atmospheric pressure, it should be something like field capacity. Don't you think? Yeah. No, no, the field capacity also is geotech. In unsaturated soil mechanics, you have that soil water, this characteristic SWCC. So from that you have this residual and the oh, okay. So next is this is what we saw, that we have an internal water, we have groundwater, then we have capillary water just above the groundwater, in which the negative core pressure is present due to the small size of the pores, and then we have intermediate water. Excuse me. Intermediate water is due to the infiltration of the rainwater below towards the groundwater, because groundwater recharges due to the infiltration of the rainwater only, And then we have soil water, which is due to which is available for plants as well as the atmospheric evaporation, transpiration, and everything. So that's the water. Now, if we talk about surface tension, we know the surface tension is a property of water that permits surface molecules to carry a tensile. This will not only, yeah, yes, the internal water, this, no, it means this water that is present inside the pores of the rock, bedrock. No, it is not structure. It's not structure. They're not talking about structural water here. They're talking about the water present in like the seams and crevices of the rock. It's called rock flow zone. Uh, groundwater, groundwater. Yeah. See, free water, free water. They are what they are saying is that free water. Why they are saying is that because this water is free to flow. It is free to cause this groundwater. If you dug a tube well, it is free to move out. It is free to be included in the aquifer, but internal water of the rocks, there is this like rock itself is not, you cannot say that rock is solid as metal. Can you say that? It still has micropores, isn't it? Micropores. Yeah. So water held in them due to the we can say tensile, the capillary forces of the rock, we can say. Okay. So when you talk about the tension, is a property that permits the surface molecule. We know when we talk about surface tension, what we are basically saying that if you have an internal molecule and external molecule, here you have a molecule that has yeah, that is in equilibrium from all sides, but at the surface, the molecules only have they have an imbalance of forces. Due to this imbalance of forces, this creates a tension. Oh, this creates a net force, a net tensile force along this surface. This is called surface tension, and it kind of makes the uh, water act like a membrane. Okay, so water molecules attract each other within the mass of water, therefore balance out at the surface. However, molecules only attracted inwards, and there will be an inward force, downward force, downward force, downward force on all the molecules, and they will form this surface tension. Okay. Attempt to contact into a minimum area, hence a drop of water is spherical. Uh, we know that surface tension of water is taken as 75 0.075 Newton per meter. Uh, and this surface tension, in fact, surface tension exists, can be shown by the familiar laboratory experiment. Uh, Water wet. So when we insert a capillary, we can see that this kind of a meniscus is formed, which is due to the inward pull. See, there is a cohesion, there is an adhesion of water particles to the outer tube, but as you move towards the center, you can see that the particles are getting moved, are getting attracted inwards because of the um, imbalance of the forces. At the ends, however, there is an adhesive force. See, because now we are talking about at a very small scale, we are talking about molecular forces. That time, even small things have to be considered. Usually, when we see a tub of water, we will not say that there is a addition along here and here. We will just say this is the level. But now we are talking about micropores. We're talking about microscopic size. So here, not microscopic size, but we're talking about like 1 mm, 2 mm size of pores. Pores will go up to microns also. So we have to take into consideration this adhesive forces, which can be significant as compared when compared to the uh, surface tension forces. So this is the effect of capillarity. Meniscus curved. Okay. So see, this is what we mentioned. If there was no uh, surface tension, the water would be like this. But because there is surface tension, there is a force T here and T here. Okay. So along this direction, there is a force because water molecules are getting attracted inwards. So if we resolve this force, we get T sine alpha, T cos alpha, and uh, we equate the force in the upward direction. T sine alpha, we say along all along this gets balanced out along the ring, along the circumference of the tube gets balanced out, but T cos alpha gets added up along the circumference, it gets added up. T, so T sine alpha, T sine alpha, T sine alpha, T sine alpha all along will get cancelled out, while T cos alpha gets added up all along the circumference. So we take T cos alpha and then multiply it with the circumference. We will get the force in the upward direction, and that is what we equate to the that is what we equate. Where is it? Yeah, T into 2 pi r cos alpha plus pi r square u is equal to 0, where u is your forward like pressure, pore pressure in the uh, water that is present in the tube. So u is equal to, we get this capillary height. Okay, now index properties. There are some questions based on that. Okay, now let's say seepage and permeability. So if you talk about soil structure, how much time has gone by? Okay. So if you talk about soil structure can be granular, it can be blocky, it can be platy. And if you see through granular soil, the path of this water is not that long. Blocky soil will have a longer path, while platy soil will have a very long path. So the permeability will be higher here, lower. Okay, so they're talking about yeah. Did I miss something? Okay. We talk about Darcy's law of permeability. Darcy saw uh, that you have this if you have a water flowing through a soil, the velocity is directly proportional to the hydraulic gradient, which is quite a logical thing to think about. Uh, we know that any kind of dynamic uh, movement will only exist if there is a difference in gradient, if there is a gradient present. For example, temperature will go from a higher temperature to lower temperature, which means that there is a temperature gradient. We know that water will go from a higher pressure to lower pressure when there is a head difference. We know that even the flow of air, it will take from a place of higher pressure to a lower pressure. There's always a gradient involved. Same is the clay, any dynamic entity. Same is the case when water, which is a dynamic entity when it is flowing, is to pass through the soil. It has to have it. If it has to flow, it has to have a gradient. If there is no gradient, there will be no water. There no motion. It will be still water, like a groundwater. Um, Not saying that groundwater doesn't move, but not at that velocity. So, if you have a gradient, uh, one second, for water to flow, if you have a gradient, what Darcy's law says is that the flow of water will be uh, the velocity of flow of water will be directly proportional to the hydraulic gradient. And what is hydraulic gradient? Hydraulic gradient is the difference in head over the length of flow. Okay, so basically what it is saying is, see, head difference we can understand. If I have connected this with the water tank, if I connect this, connect this, all these three will have same head difference. But what will be the difference is the length of flow. Okay, the length of flow. So here they are trying to say the length of flow is short, length of flow is long, length of flow is very long. Okay, excuse me. So what we talk about here is total head is equal to, okay, the total head is elevation head, pressure head, and velocity head. This we know from fluid dynamics. And velocity head usually we don't take v square by 2g. Usually we take pressure head and elevation head, because velocity usually is very small as compared to the pressure head. So head at A equals ZA plus HA, head at B is equal to ZB plus HB. Loss of head delta H is equal to ZA plus HA minus ZB plus HB. This is the hydraulic gradient. Okay. Okay, so this is the pressure head, this is the elevation head, this is the pressure head, this is the elevation head. Okay, so the flow will take place from A to B, and what Darcy's law says is that the velocity of the flow will be directly proportional to delta H over L. The formula most often used is one produced by Hazen that we were just talking about, K is equal to 10 times d10 square, where K is in mm per second, d10 is effective size in mm. Typical values of permeability, we can see that value of permeability is high for gravel, and it just decreases as we go down, because as we go to finer soils, the size of the pores is reducing. And you know, when we used to study fluid mechanics, there is a frictional force between the walls of the uh, uh, like there is a frictional flow, and there is a boundary line we used to have that we have to study. And as the force would be maximum at the velocity would be maximum of the at the center, and if more and more area of flow is dedicated to this formation of boundary line, and this we will get a smaller velocity. Okay, Factors affecting coefficient of permeability, we already know that shape and size of the soil particles. Why? Because we saw that if you have uh, flaky particles, if you have granular particles, if you have blocky particles, it's not necessary that flaky particles will only always have it's actually not correct. Uh, Flaky particles will not necessarily have low um, permeability. It will depend upon the texture of the soil. It should have written here texture because you can have a flocculated structure, you can have a dispersed structure. Flaky particles with a dispersed structure specifically will have lower permeability, while flocculated particles will have higher permeability. The void ratio, permeability increases with increase in void ratio, as you mentioned, uh, in same soil. Okay. Degree of saturation, permeability increases with increase in degree of saturation. Is this correct? Is this correct? Permeability increases with increase in degree of saturation. Okay. Just a moment. Ow. Let me check. I have this. Just a moment. Yes. Yes, that's fine. Yeah. Okay, and composition of soil particles for sands and silts is not water. However, for soils with clay minerals, it's one of the most important factors. Permeability in this case depends on the thickness of the water, the double diffused layer that we call, which is a function of the cation exchange capacity, valence on cations, and other factors remaining the same. Coefficient of permeability decreases with increasing thickness of the diffused double layer. Okay, this is about composition of the soil particle, basically the clay mineralogy. Then seepage and permeability factors, structure, finely and solid flocculated structure, high coefficient of permeability than dispersed structure. Increasing dispersion, permeability decreases. Viscosity of the permeant, if the viscosity is high, permeability will be low. Density and concentration of permeant, uh, okay. Then like almost same. Okay. Determination of permeability in lab we do using Falling Head method for finding. for fine grained soils and constant head method for coarse grained soils. So we'll not go through the test methods. Pumping in test, pumping out test, packet test, and bore filter. So these are the field methods in which we take a bore well and we pump. For example, we have a groundwater here, and we pump out and we take other wells and we check the change in level of water based on the suction provided here. So this is the constant this is the constant head test, this is the falling head test. So falling head test we do for fine grained soils because uh, the the water level decreases at a lower rate in the standpipe that we are checking for your experimental, we are taking experimental values on the standpipe, how much water has flown in what time. Falling at permeability test is done for fine grain soils because this fall in water level is very slow in permeability in fine grain soils as compared to coarse grain soils. If we do these in coarse grain soil, we will not even have time to uh, uh, clock the rate of decrease in the height of water in standpipe. And because of this, we have to take in coarse grain soil. What we do is we create a steady state condition in which the inflow of water is equal to the outflow of water, such that the water level is always this is always saturated. And what we here calculate is the discharge uh, uh, per unit time. We take calculate the discharge, and based on that we make our calculations. And also we have to know the head. Okay, so seepage and permeability, we talked about the Darcy's law. Q is equal to Ki is equal to Vi, and V can be written as V is equal to Ki, and V can be written as Q by A, and we have Q is equal to KIA, where K is the coefficient of permeability, A is the area of flow, and I is your hydraulic gradient. So K is obtained from this expression. Let us now talk about the tests. Field permeability, we saw a pumping test. We are taking this test well, and then we're taking observation wells. And in the test well, we are creating pumping out some water, and then at uh, different wells, we are monitoring the level. So what will happen is that it will try to raise equilibrate. So based on that time and distance from the well, we calculate the probability. Okay, so as I mentioned earlier, that soils are anisotropic, they're not isotropic because they have sedimentary type of deposits. So when we have a sedimentary type of deposit, these layers will be homogeneous in itself. They have same properties, but the different layers will have different properties. So they become anisotropic. So isotropic is a material that has same properties in all directions, but this material is not having same properties in all directions. It may have a same, like one layer will have same properties, but not the entire material. Okay. A sedimentary deposit may consist of several soils, and it is often necessary to determine the average values of permeability in two directions, one parallel to the bedding plane and other right angles to the bedding plane. Bedding plane is the direction of this layers. Let there be n layers of thickness S1 to n. and total thickness be h, and these be the representative coefficient of permeabilities parallel to the bedding plane, and kxe be the average permeability parallel to the bedding plane. Considering flow parallel to a bedding plane, we can take it as average, where A is the total area. Okay, but total flow is equal to flow through each layer. From based on this, we take equilibrium. From based on this, we calculate the uh, horizontal and vertical permeability. Okay, I hope I'm not running too fast, but let's move on. Equation of flow through soil. This is how we used to do this uh, continuity equation. We take a small area unit of unit volume, and we talk about the flow, and then we impose the equilibrium conditions, and from there we will get the flow through the material. The only thing is that in water, when we used to do that, there was not any uh, fall of head when moving from this body to this. Here we are talking about head fall, hydraulic gradient, change in hydraulic gradient. So this is our equation. So in when we used to do the continuity equation for water, we did not have different permeability. We did not have permeability here. Why? Because there was not fall of head due to uh, like fall of head was due to, it could be due to elevation change, or change in velocity, change in pressure. But where all the three are same, elevation is same, velocity same, pressure is same, for example, then there will be no flow. But here we're talking about, when we talked about in water, the head from here and here can be can change due to, for example, pressure, difference in pressure. But in soils, it changes due to specific, usually due to this internal losses uh, that we attribute, that uh, we can correlate to the permeability or the porosity of the fluid of the material. So we get this continuity equation in this form. And if we have a isotropic material, kxyz is equal to k, then we get this kind of equation, which we used to get in water also. But because soil is usually anisotropic, we have to have a kx and kz attached to it. And here what we do usually is we divide this by kx, remove it from here, and we transform this coordinate. The second coordinate we transform, so that we get this kind of an equation. And we know that this is a Laplace equation. Uh, okay, we know that this is a Laplace equation, and Laplace equation has solutions in the form of streamlines and potential lines, and we get a flow line, we get equipotential lines, and we form flow nets based on these kind of flow nets. There are some rules. For example, the flow lines should be perpendicular to the streamlines wherever they are cutting. Other thing is that the aspect ratio of this should be square aspect ratio, as in it can be like this also, but the this length divided by this length should be same for all the mesh art mesh units. The other thing is that the water will flow along the flow lines and not never perpendicular. Like there cannot be any flow uh, cross to the what can I say, mm, equipotential lines. Yeah. So based on that, what we do is we make these flow nets. Uh, Usually, what I used to get tensed about it that it is so arbitrary. If I take five flow lines and somebody is taking three flow lines, that we will get different answer. But that is not it. Why? Because if I take five flow lines, for example, like this, this, I'll also have to take more number of potential drops so as this aspect ratio becomes same. So what it boils down is that whatever number of flow lines you take, you will end up with the same NF by ND ratio, number of flow lines by number of potential drop ratio, and that is what matters, not how many actual flow lines there are. Okay, if you draw it properly. Okay, so yeah, as I was saying, Q is equivalent to NF by ND into K into H, which is the head drop per unit per total head loss. Then we're talking about permeability and seepage. Okay, where they are uh, used. For example, we have a dam, we have an embankment. What happens in this embankment is that the water will seep like this. Okay, and there is an exit. Impermeable membrane is this. So the water will cause a toe failure here. But if we have a sheet pile here, the flow of water will, uh, oh, it is what it is shown. Yeah, here the flow of water will change. Otherwise, we could have a piping failure here. And this is what I was saying, that if we have an anisotropic, material, what we do is we take this Kx and Kz ratio and we transform the coordinate xt, where xt is equal to Kx Kz by 1 by x, and we transform the whole thing and we get, instead of plotting x, we plot xt. We make the flow net, we calculate whatever we need to calculate, and then from after calculating, we put xt back equal to x. This is now a Laplacian. See, by doing this, we will convert this equation, which is not a Laplacian equation, into a Laplacian equation. Seepage quantity in an anisotropic soil. Uh, this is exactly as before. Only problem is that what value of K to use. See, here uh, in anisotropic soil, we used K, but in anisotropic soil, because the properties in both directions are not same, we have to take and a K equivalent, and this is the K that we have to take. Critical hydraulic gradient. Critical hydraulic gradient, you have to know is that you have, for example, you have a soil deposit and water is acting from above. What it is technically doing is that it is uh, uh, kind of the soil particles have a downward force of due to under gravity, and if you equalize this force, these particles will become like at a net zero. They will start floating, kind of thing, if you understand. um, Kind of a buoyant force, kind of a buoyant force. When you go in water, the water makes your weight less. You make you weigh less. That is what's happening in these particles. They are weighing less, and if the if the seepage pressure is high enough, what can happen is that they can become like um, they can act as a fluid. That is what happens when you have liquefaction of sand, especially in earthquake zones, or when you have quicksand, and this is an quicksand, and this is liquefaction sand is an example of this critical hydraulic gradient, which is the minimum gradient that required for the soil to flow. Okay. So downward force is buoyant unit weight into volume. Upward forces is the seepage force, and we equate them, and from there we can get the critical hydraulic gradient. The hydraulic gradient should not be as high as critical hydraulic gradient, otherwise we will have failures like piping failures or liquefaction. Okay, these are some questions. Okay, so now, excuse me, uh, can we take a break for 5 minutes?